be thought of as an encouragement that you personally should attempt to construct anything shown or discussed here, as this presentation is for information purposes only. We live surrounded by an energy field of effectively unlimited power. We can access that power for our own use in more than 20 different ways. As already has been discussed in a previous video presentation, it's perfectly possible to draw energy from an aerial-earth combination. You don't want to have a tuned circuit like a radio receiver, as that restricts the power to less than that of one radio station. Instead, you want wideband reception, which pulls in power from the sun-charged ionosphere and from the 200 lightning strikes per second around the world. There are many excellent designs from developers such as Jez, AlexCore and Dragon, and a basic module for receiving power from an aerial is as shown here. You have a drum forming the main aerial with a single strand of wire coming down, and the signal that comes from there passes through the circuitry to the earth connection. But as it passes through the circuitry, it is transformed into direct current by 4 diodes, preferably germanium diodes like 1N34, and the electricity produced is stored in 2 different electrolytic capacitors to give you an output of a plus and a minus in direct current. Jez uses a shiny insulated metal plate as a good receiver antenna, although these early aerial descriptions are relatively low power. His aluminium plate is 800 by 600 by 2 millimeters, and it's suspended inside the attic of the house where he lives, and they're suspended on plastic ties, which are effectively twisted nylon rope looped round to hold the thing up without actually having an electrical connection to it. You can have as many modules as you like connected to any one aerial. Ideally, they should be halfway between the top of the aerial and the actual earthing point. Generally speaking, it's better to have 2 earthing points as shown here, and you can have as many modules as you like connected between the aerial and the earth, and the power increases with each additional module. Normally you use germanium diodes because they have a very small voltage drop across them, typically about 0.2 volts. But you can increase the output of the module by using extra components as shown here. 4 diodes on each side, giving you a total of 8 diodes, 4 small capacitors, and the original 2 electrolytic capacitors. That particular arrangement doubles the output for each module. Dragon put 100 of those original modules together on 2 boards, which he arranged like this, and the output from the 2 boards was 96 watts continuously. The AlexCore aerial system is slightly different. Like Thomas Henry Moray, he uses a horizontal aerial of 60 meters or more, and then a vertical wire coming down to the circuit, which is then carried on to the earth connection, and he uses that circuit to charge a battery. The longer the aerial, or the greater the number of aerials used, the greater the rate of charging. It's suggested that the aerial should be connected between the eaves of a house and a nearby tree, and the aerial wire should be 0.5 millimeter diameter or thicker, and it needs to be insulated from its supports, and you can use plastic cord for that. A more powerful version of a circuit can charge 12-volt batteries. His horizontal aerial comes down to feed 3 separate modules, which rectify it and pass the charge to a 400 volt 100 microfarad capacitor. The voltage on the capacitor builds up and up and up until it exceeds the strike voltage of a neon bulb, which is typically 90 to 110 volts, plus obviously the 12 volts of the battery. But when that happens, the neon lights up and feeds the silicon control rectifier, which is a BT151800R, as shown here, and that fires the charge from the capacitor into the battery, and that's an effective way of charging a battery. There is a much more powerful system which is highly dangerous effectively. People often ask for a free energy generator that will give them 10 kilowatts, but they have no notion of the power that's actually involved in 10 kilowatts. If you think of 10 kilowatts being drawn from your wall socket, if you've got a 220 volt local supply, as most of the world does, then each kilowatt's about 5 amps, and 10 kilowatts with about 50 amps flowing at 220 volts at the low frequency of about 50 cycles a second. And that's conventional hot electricity, and it will kill you. There's no question about that, unless you're very lucky. If you connect your arms across the output from a wall socket, it will actually kill you. In the case of American power supplies, the wall socket will only be giving 110 volts, but the current will have to be twice that to compensate for the amount of kilowatt hours that's been drawn. So instead of 50 amps, you're talking 100 amps. Both systems are highly dangerous. Lawrence Rayburn of Canada has developed an aerial system which is very powerful. He calls it the TREC. It pulls out 10 kilowatts of energy, and it is something that can definitely kill you if you're careless with it. The aerial system is 2 4-foot diameter spirals made from 3/4 inch soft copper pipe. Each spiral is sandwiched between 2 sheets of Lexan plastic. They're mounted 30 feet apart vertically. The objective is to create a tuned path to the ionosphere and so draw down some of the massive amount of excess electrical power that's there. There is a spark gap and a multiple tuning coils, and voltages of 600 volts get generated in the circuit before the output is adjusted to what's convenient. A substantial earthing plate of at least 16 square feet is needed, and wire which is able to carry serious loads has to be used. A signal generator is used to modulate the power and give you the mains frequency that you want. This is the general circuit. You have a powerful earth system there, 16 square feet buried in damp earth. You have the 2 spiral coils of copper wire connected with a wire between them, actually connected with 2 wires between them. One has a spark gap, the other one is broken halfway to feed the independent tuning coil system that's been used here. The output that comes from that is powerful, and a little signal generator is used to modulate the power to the frequency you want. And that output transformer here has to be very powerful. It has to be rated to carry 10 kilowatts, which is what you can get out of that system. The circuit is high power, and as I said before, it can kill you, just as your mains wall socket can kill you if you're being careless. While this information is useful, it is a very long way from everything which can be known about the subject. As a low power high voltage source, for example like the Testatica machine designed by Paul Bowman of Switzerland, is a self-powered 3 kilowatt output generator. It uses electrostatic output of a Wimshurst machine as its input. The general configuration is interesting. He's made his own Wimshurst style machine. It has two diagonal bars, one on the front and one on the back, to pick up output, which is fed to Leyden jar capacitors, and then that output is fed on to whatever circuitry Paul uses to deal with that sort of output. The output is also drawn from passive electromagnetic coil electromagnets, effectively, which are passed to a crystal capacitor feeding the power out. But those coils also pass power back to two diagonal sloping drive bars, one on the front, one on the back. And those bars, once you get the capacitor plates moving and generate some power in these electromagnets, keeps the disc itself rotating all on its own. The discs are made of acrylic plastic. They have 50 identical steel segments attached to the plastic plate, and that's the way that this particular input is passed to the Paul Bowman machine, which is also known as the ML system. Now, the rotation is self-propelled, but the serious power that you can get comes from the atmosphere itself, from the ionosphere. Another German who's called Hermann Plausen presented a great deal of practical information in his 1925 patent, which is US 1540998, entitled Conversion of Atmospheric Electrical Energy. Hermann describes a system with 100 kilowatts of output as being a small system, but a system of that size will almost certainly have many aerials providing the input. He says the static electricity which runs to Earth through aerial conductors in the form of direct current is of very high voltage and low current strength, but can be converted into electrodynamic energy in the form of high frequency vibrations, which is a fancy way of saying powerful AC power. He shows figure 1 here, which is a simple method for converting static electricity as coming from the Wimshurst machine, which he shows here just for simplicity. The output from that is the same as from an aerial. He has a spark gap here between 0.7 and 8, and when a spark occurs there, the effect through this circuit here is very, very marked. Goes through two capacitors and through the primary winding of a step-down transformer. Now, the step-down transformer is very useful in that it lowers the extremely high voltage to a much lower and more useful level, and doing that it also raises the available current from it. In the times when he was dealing with these things, there were very few aircraft. You remember that it was around 1903 that the first heavier than air aircraft got off the ground, and so at that time tall aerials would not have been considered a hazard, and Hermann clearly had tall aerials in his installations. He mentions anything from 300 meters to 5,000 meters, which is like 15,000 feet and well within the range of flying aircraft. But in figure 2 here he shows aerial input going to a spark gap, which is 7, and he has an arrangement here across the spark gap, so if the spark gap gets to its limit in current carrying capacity, the additional line will fire with its 3 separate spark gaps in it, and feed any excess power through safely to the ground. Like the Wimshurst machine, he's got two capacitors across the spark gap and a step-down transformer which feeds the load. It can also feed an electrostatic motor if you want. Just in passing, the reason for the extra safety spark gaps is that there's always a possibility of either a direct lightning strike hitting the aerial or striking the ground nearby, and that creates a tremendous surge of electrical energy in the area, because a lightning strike is like 10,000 amps at millions of volts, and it creates a very marked disturbance in the general area. And by disturbance I mean electromagnetic disturbance rather than just the heated air, which creates a tremendous bang that can be heard from miles away, known as thunder, as you know. Right, in figure 3 he shows an arrangement here where he has wound a choke using the aerial wire round a toroid, which is made of very thin iron strips which are insulated from each other to form a good magnetic core to his choke. He has, as before, a multi-gap safety spark gap, and he's opted for a dual spark gap here in the middle, and he feeds it off to an electrostatic motor. Now, you may not be familiar with electrostatic motors, but they work extremely well. You'll find on the web quite an amount of information on them. This one here on the left is a 3D printer homemade version, and supplied to there makes it rotate very nicely. This is a commercial version, which is a much more powerful animal, and the positive electric charge collected from the aerial tends to combine with the negative electricity connected through the earth wire, and they produce a very considerable drive, which he considers is the best way to take power off an aerial, or certainly a very effective way to take power off an aerial. In figure 4 here, the spark gap 7 is shunted across the capacitors 5 and 6, and it feeds the motor M, which is 1 and 2. That's the sort of system that's very convenient. It can be improved on, though, by using a fixed star-shaped central electrode which is connected to the earth wire, and an external or exterior larger star-shaped spark gap which is driven by a motor which isn't shown in this diagram, and it's fed through the aerial and through an aerial choke, and has a safety spark gap of many gaps across it. And the rest is the same then. You've got capacitors 5 and 6 feeding the primary of a step-down transformer to give an output there, and you can use the large electrical output from a system like that to provide heating and lighting. The main difference is the star-shaped disc, and that creates multiple spark gaps and sparks from this system. It's something that's quite difficult to say, but it is an effective way of dealing with the situation. An alternative way is shown in figure 6, where you have the load connected across a variable coil. Nowadays variable coils aren't used very much. They were in the early days used very nicely with crystal radio sets, radio receivers, and they could be wound and made quite conveniently. They look commercially, if they get one nowadays, they would look like this. You've got an insulating central tube, which is typically porcelain, and you have a slider which has got spring contacts pressing against a strip of the turns of this coil of wire, which has the installation removed from it. So the position of the slider up and down the coil sets the number of turns between the tap in the middle and either end. And that's what's used here in figure 6. The tap on the coil feeds to an electrostatic motor, and again you have the bypass of a multiple spark gap there. But typically speaking, it's very effective the way that it's going. Spark gap 7, the working spark gap, is there between the part of the coil that you have in use and the electrostatic motor. Now, there are many other ways of dealing with this, and as this patent explanation continues, it's very interesting. Herman's patent is more like a tutorial in the practice of drawing electricity from the atmosphere, and he's clearly very experienced in this series of techniques. He keeps on mentioning in his patent that such and such has been shown in practice to do XYZ, which is impressive because it's not written in this normal style of a patent where people are trying to conceal how to do things. But here anyway, he says in figure 10 it shows a motor circuit with purely inductive coupling. In other words, you have your safety spark gap set there, your spark gap here, and you've got the two coils as before and the transformer that feeds the power out, and that power goes to an electrostatic motor. It can be connected in various ways, and the figure 11 here shows the actual electrostatic motor connected there. In all of these cases you have an aerial choke, which is a safety feature again against nearby lightning strikes. In figure 12 you have the similar arrangement, but here you're using two transformers and the spark gap and the safety spark gap in the middle feeding your electrostatic motor. The diagrams so far allow motors of low to medium strength to be operated. For large systems, however, they are too inconvenient, as the construction of two or more oscillation circuits for large amounts of energy is difficult. The governing is still more difficult, and the danger in switching on or off is greater. Figure 13 shows a means for overcoming such difficulties. The oscillation circuit shown here runs from point X through the capacitors 5 and 6. Is that right? No, it's only capacitor 5. Through capacitor 5 and through the variable coil 9 and through the spark gap 7 and the two segments 3A and 4A, which are round the outside here, which form the arms of a Wheatstone bridge, and then back to X again. If the motor is connected by brushes 3 and 4 transversely to the two arms of the bridge as shown, electromagnetic oscillations of equal sign are induced in the stator surfaces 1 and 2, and the motor does not revolve. If, however, the brushes 3 and 4 are moved in common with the connecting wires 1 and 2, which connect the brushes to the stator poles, a certain alteration or displacement of the polarity is achieved, and the motor starts to revolve. The maximum action will result if one brush 3 comes on the central sparking contact 7 and the other brush 4 on part X. In practice, however, they're usually brought onto the central contact 7, but only held in the paths of the bridge segments 4A and 3A in order to avoid connecting the spark gaps with the motor oscillation circuit. Now in figure 14, it's better where the motor is not directly wired to the segments of the commutator, but instead it's wired to the secondary coil 10, which receives induced power from primary coil 9. This arrangement provides a good transforming action, a loose coupling, and an oscillation circuit without a spark gap. Let me point that out again. This figure 14, is a circuit which is very effective. Figure 15 has the motor wired directly to the primary coil at X and X1 in the same way as an autotransformer. Figure 16, instead of an inductor, capacitor 6 replaces the inductance and is inserted between segments 3A and 4A. This is the advantage that the segments 3A and 4A need not be made of solid metal, but can be made out of spiral coils which allow a more exact regulation, and high inductance motors can be used. We come now to figures 17, 18 and 19. They may be used with resonance, particularly with the induction capacitor motors between the large stator induction capacitor surfaces. Small reversing capacitors are connected, and they're connected to earth. Such reversing poles have the advantage that with large quantities of electrical energy, the spark formation between the separate oscillation circuits cease. Figure 19 shows another method which prevents high-frequency electromagnetic oscillations formed in the oscillation circuit feeding back to the area. It's based on the well-known principle that a mercury lamp, one electrode of which is formed of mercury, the other of solid metal, such as steel, allows an electric charge to pass in only one direction, from the mercury to the steel, and not vice versa. In other words, it is a diode, a very powerful diode. The mercury electrode of the vacuum tube N is therefore connected to the aerial, and the steel electrode is connected to the oscillator circuit. Charges then can only flow from the aerial through the vacuum tube to the oscillation circuit, and no flow occurs in the opposite direction. In practice, these vacuum tubes must be connected behind an aerial choke, as on their own they do not protect against the danger of lightning. The systems that Herman speaks of are very serious power supply systems, and he says as regards the use of spark gaps, all arrangements as used for wireless telegraphy may be used. Of course, the spark gaps in large machines must have a sufficiently large surface. In very large stations they are cooled in liquid carbonic acid, or better still in liquid nitrogen or liquid hydrogen. The spark gap casings must also be insulated and be of sufficient strength to be able to resist any pressure which may arise. Any undesirable excess superpressure which may be formed or generated must be let off automatically. He says, I have employed with very good results mercury electrodes which were frozen in liquid carbonic acid, the cooling being maintained during the operation from the outside through the walls. Now figure 20 shows one of the most simple forms of construction of an aerial network in combination with collectors, transformers and the like. E is the earth wire, 8 is the safety spark gap, 7 is the working spark gap, and 1 and 2 are the stator surfaces of the motor, which is motor number 5. You've got a combination here, a circular arrangement with balloons supported, or maybe I should say supporting, the wiring and metal of their own surface. The technique for getting a lot of charge onto an aerial, one of the best methods is allowing the wind to blow past a metallic surface, and that generates electrostatic charge of large amounts on the metal surface. In actual collectors, most of the metal sheets are preferably made of aluminium and magnesium alloy. They're filled with hydrogen or helium and attached to copper-plated steel wires. The size of the balloon is selected so that the actual weight of the balloon and its supporting wire is supported by the balloon. Aluminium spikes made and gilded as described below are arranged on top of the balloons in order to produce a conductor action. Small quantities of radium preparations, more particularly polonium ionium or mesothorium preparations, considerably increase the ionization and so increase the performance of these collectors. In addition to metal balloons, fabric balloons which are sprayed with a metallic coating may also be used. Instead of the ordinary round balloons, elongated cigar-shaped ones may also be used. In order to utilize the frictional energy of the wind, patches or strips of non-conducting substances which produce electricity by friction may be attached to the metallized balloon surfaces. The wind will impart a portion of its energy in the form of frictional electricity to the balloon casings, thus substantially increasing the collection effect. In practice, however, very high towers of up to 300 meters may be employed as antennae. In these towers, copper tubes rise freely further above the top of the tower. A gas lamp secured against the wind is then lit at the point of the copper tube, and netting is secured to the copper tube over the flame of the lamp to form a collector. The gas is conveyed through the interior of the tube up to the summit. The copper tube must be absolutely protected from moisture at the place where it enters the tower, and rain must be prevented from running down the walls of the tower, which might lead to a bad catastrophe. This is done by bell-shaped enlargements which expand downwards, being arranged in the tower in the form of high-voltage insulators or Siamese pagodas. In order to collect large quantities of electricity with few aerials, it is as well to provide the aerial conductor with sets of capacitors, as shown in the two methods of construction in Figures 21 and Figure 22. In Figure 21, the set of capacitors 5 is connected between the aerials Z, which are these balloons here, via lead A, and a ring connector to point C, which then feeds on down to the rectification circuitry. If two such aerial arrays have a large voltage difference, then that can be dealt with by connecting sufficiently large capacitor sets, which are 5, 5A, 5B and so on, by means of star conductors D and D1, which are here. Figure 23 shows a connection of three such rings of collectors positioned in a triangle with a central set of capacitors. Capacitor sets of such large installations must be embedded in liquefied gases. In such cases, a portion of the atmospheric energy must be used for liquefying these gases. It's also preferable to employ pressure. By this means, the capacitor surfaces can be reduced in area and still allow the storage of large quantities of energy. This secures against breakdown. For the smaller installations, the immersing of the capacitors in well-insulated oil or the like is sufficient. Solid substances cannot be employed as insulators. The arrangement in the diagram shown earlier has always shown both poles of the capacitors connected to the aerial conductors. An improved method of connection has been found to be very advantageous. In this method, only one pole of each capacitor is connected to the collecting network. Such a method of connection is very important, as by means of it a constant current and an increase in normal working voltage is obtained. If, for example, a collecting balloon aerial, which is allowed to rise to a height of 300 meters, shows 40,000 volts above earth voltage, in practice it has been found that the working voltage, with a withdrawal of the power as described earlier by means of oscillating spark gaps and the like, is only about 400 volts. If, however, the capacity of the capacitor surfaces is increased, which in the above mentioned case was equal to that of the surface of the collectors of the balloon aerials, to double the amount of electricity available by connecting the capacitors with only one pole. The voltage then rises with an equal withdrawal of current up to and beyond 500 volts. This can only be ascribed to the favourable action of the method of connecting only one side of the capacitors. In addition to this substantial improvement, it's been found to be preferable to insert double inductances with chokes and to place the capacitors preferably between two such chokes. It's also been found that the useful action of such capacitors can be further increased if an induction coil is connected as an inductive resistance to the unconnected pole of the capacitor, or still better, if the capacitor itself be made as an induction capacitor. Such a capacitor may be compared to a spring. When compressed, carries itself an accumulated force which it gives off again when released. In charging, a charge with reverse sign is formed at the other free capacitor pole, and if a short circuit occurs through the spark gap, the accumulated energy is again given back, since now new quantities of energy are induced at the capacitor pole connected to the conductor network, which in fact charges with opposite sign to that of the free capacitor pole. The new whole voltage energy in the aerial is thereby increased. In the same time interval, larger quantities of energy are accumulated than would be the case if such capacitor sets were omitted. There is substantially more advanced information in the patent, which, as I mentioned, seems to be more of a tutorial based on extensive experience rather than on a conventional patent would be.